Hello everyone, in this video we're going to discuss the buddy system code. So you can see here we have included the header files, there are some global variable declarations, there are some function declarations, and then to start with main we are declaring some local variables, and then we are printing this message buddy system requirements, and then we are asking the user to enter the total available memory, which in our example was 1024, right? So we are asking the user to enter the total available memory. And then you can see there's an infinite for loop. In this infinite for loop, first thing we are doing is we are printing a menu. In this menu, option 1 is to allocate the process memory, option 2 is to release or remove the process from the memory, option 3 is printing the tree structure of the memory allocation. Option 4 is to exit, and we are asking the user to enter the choice. We are reading the choice here, right? And then we are using a switch case, and the case 1 is to allocate the memory, right? Memory allocation. We are asking the user to case 1 is memory allocation. We are asking the user to enter the size of the process or the requested memory, right? We are reading the request, and then we are calling function segment alloc, and this function takes two arguments, the total available memory and the request. So segment alloc function is for memory allocation. Then coming to case 2 is memory deallocation. We are asking the user to enter the request that is to be released, and then we are reading the request, and we are using function make free to release the memory. So this make free function takes the requested size to be deallocated as an argument. Then case 3 is display the memory allocation map, and we are using a function with name printing, and we are passing the total size and 0 as an argument. The 0 here indicates that we are starting from the root node of the tree, so level 0 of the tree, hence we are passing 0 here. Now let's see each of these function in detail. So coming to segment alloc function. So segment alloc function, it's taking the total memory and the requested memory as an argument. First thing we are doing is we are saving the total into a temporary variable called size. So size contains the total memory that we have received from the main function, and we are starting the level. We are initializing f level to 0, indicating we are starting from the root node. Now the first is an error checking. So if our requested size is more than the total available memory, then we are printing the message system does not have enough memory, because the memory that we have requested, it is more than the total available memory. And then we are returning. We are printing this error message system does not have enough memory, and we are returning. The next step is in segment alloc is to split the partition into half. So you can see here there's a very interesting condition here. If our requested memory, if it is less than size, and the requested memory is more than half of the size, we found the partition to be allocated, right? It should be less than the size. At the same time, you should not be able to further split the partition. Then it indicates that the request is more than half of it. Then we stop, we found the partition, and we come out of this infinite while loop. Else what we are going to do? We are going to split the partition into half. Size is equals to size by 2. And then we are increasing the level of the tree. We are going one level down the tree, right? So this process is continued until we find a suitable partition. Let's understand this particular code with this image here. Let's understand this with this image. So say for example our request is 100 is less than 1024, hence it is split into 512, 512, and 100 is less than 512, it is split into 56, 256, 100 is less than 256, it's split into 128 and 128. Now 100 is less than 128, but 100 is more than half of it, 64. 100 is more than 64, hence we will not be able to we should not be able to split this further, and this is the partition that is to be allocated to our request of memory 100, right? So this we have to place our request 100 here. Now the next step, we found the partition. Now we have to allocate the partition. So during the allocation of the partition, we are doing two things. One is we are checking if initially all the partitions will have 0, indicating that it has not been allocated, right? Once the partition is allocated, we are placing that request there. Say for example, in this case 100, we will write 100 here. So to check if the partition is free, we are checking two conditions: if that location value is 0, and also the second condition is its parent has not been allocated. So in case, say for example, this 256 is already allocated to some other process, then there is no point in using these two partitions, because this has already been allocated. It is not free, it is not available. So So we check these conditions. We will look into the code. So one is that location is empty and its parent has not already been allocated. And after allocating the partition, what we are doing is we are indicating that that parent node has already been splitted. So we place a marker 1 indicating that that request has already been allocated. For example, look at this, 100 has been allocated. I will write 100 here. And now its parent, this node has already been splitted into 128 and 128, right? So I will write 1 here. And this node has been splitted, hence I place a marker here 1. And this node has already been splitted, I place a marker 1 here. So the segment alloc function, what we are doing is we are once we get the partition, we write the we see if that partition is free and its parent is already not been allocated, then we write the requested value here, and all of its parents are marked as 1 1 1 1, indicating that that particular node has already been splitted. Now this implementation of binary buddy uses a binary tree, as you have already seen. So we are using an array implementation to implement this. So in array implementation, for a given node, if say this is the node, right? If our parent node is at 0, then its left child will be here and its right child will be here. Now for this particular node, which is at 1, its left child will be at location 3 and at location 4, right? And for this it will be 5 and 6, right? So for example, for any given node I, its left child will be at position 2i plus 1 and its right child will be at position 2i plus 2. You can calculate this, right? And in reverse, for a left child, its parent will be at location I by 2 and its right child will be at location I minus 1 by 2. You can verify these things. So we require this particular thing here. For a left child, its parent will be at I by 2 and its right child will be at position I minus 1 by 2. So if this, I consider this as a binary tree, the you can see this node is at location 0, 1, 2, 3, 4, and this node's left child 5, and this node's right child 6. This will be 7, 8, 9, 10, and so on. So like this, the binary tree is represented using array. Okay. Now let's go back to the code. So once we have seen this array function and then the splitting function. Once we have the partition where it is to be allocated, here coming to this for loop, you can see. So this for loop, it is starting with I is equals to 2 to the power f level minus 1 to I less than 2 to the power f level plus 1 minus 2. So what does this is? It is for a given level. You have identified the level in which the request can be satisfied, right? So in that particular level, in that given particular level, you are checking which of the node is you're going to check all the levels in that particular node. Say for example, if my level was this, I mean the partition that I found can be allocated is at level 1, then it's going to check if this node can be allocated. If this node cannot be allocated, it's going to check with this node, right? If it is this level, it's going to check this node. If this node cannot be allocated, it's going to check this node. If this node cannot be allocated, it's going to check this node's left child and then further this node's right child. So at a given level, it's going to check all the nodes in that particular level. Hence the for loop condition, 2 to the power f level minus 1 to 2 to the power f level plus 1 minus 2. Okay, so in this for loop, we are checking if we are allocating the request, right? So I'm checking if the tree of I is equal to 0. In that means that partition is free. It has not already been allocated. And place of I. So what is this place of I function doing is, it is checking if its parent is not already been allocated. Okay, and we will look into this place function immediately. So if these two conditions are true, that is tree of I is equal to 0 and place of I returns true, true and true, we come inside. First thing we do is we are going to write the request to the tree index. And then we are using a function make divided. So as I have already told, right, once we write the request, we have to mark its parent node as 1, indicating that node has already been splitted. Okay, so we will look into place and make divider function, and once this is done, we print a message successful allocation, and we break from this for loop. If not, we are going to suppose if one of these two conditions are not true, then we go to the next node in the tree and we check this conditions and repeat that for the next node in the tree if one of these two conditions are false. Now let's look into this place function and make divider function. These two codes are very similar, right? So given a node, we are checking if until the node is not equal to 0, until we reach the node. So if the node is left child, then its parent is node minus 1 by 2 node, if otherwise it will be node divided by 2. So basically we are, for a given node, we are taking the index of the parent and we are checking if that index is greater than 0. So when do we have the value greater than 0? When that particular partition has already been allocated, right? In that case, we return 0, we return false. If the parent has already been allocated, we return false. So this we are going to check until the root level, right? So if for any of its parent has already been allocated, we return false. If none of the parent has already been allocated, then we return true, indicating that the node can be placed there. Make divider function has a similar code. As you can see, it's taking node is until node is not equal to 0, we are extracting the parent node index, and we are writing 1 in that parent node. So for all of the parent, we are going to mark 1 1 1, indicating that has already been splitted, right? So this is place and make divider function. So coming again, we check if tree of I is equal to 0 and it can be placed. We write the request in that index, and then we are calling make divider function, which basically writes 1 in all of its parent and prints successful. Now and then it comes out of the for loop, right? So now if none of the nodes in that particular level are free, then we reach this condition and we have to print a message does not have enough memory. So and this is and that's done. We are done with the segment alloc function. So in segment alloc function, we are basically first checking if the requested size is greater than the total size. We print the message system not enough memory, and then we partition it. Once we get the partition, we check if the check for all the nodes in that particular level, if that node is free and it can be placed there. If so, we write the request and mark its parent. Otherwise, we go to the next node in that particular level and repeat this procedure. If none of the particular nodes are available, we reach this condition and we print does not have enough memory. So this is about segment alloc function. Now make free function. So what is make free function does is, first thing is this in make free function, the step 1 is we are checking for that particular request for each of the node. So it's a linear search. Okay, so we are taking the request, right? We are comparing that request with the tree node index. We are, if it is equal, we have found the node to be deallocated, else simply increment the increment to the next node. Basically it's a linear search. We are searching for that particular request in the tree, and when we found that particular node, we are breaking, else we are going to move to the next node for the comparison. So this is basically linear search. Once we found the node, we are writing tree of node equal to 0, indicating the memory has already been memory is released in so that particular node has been written with request value, right? Now we are writing 0, indicating that it's freed now. Now what we have to do is we have to check when we are releasing the memory, we are checking if it's buddy node. What do you mean by buddy node? Is say these two are buddy nodes, these two are buddy nodes, these two are buddy nodes. So in make free, what we do is what we do is, if these two nodes, say I'm releasing 256 here. Say for example, this is the node which is allocated. I'm releasing 256. When I release 256, if I check if its buddy node is free. So here you can see this its buddy is free, isn't it? So I merge these two nodes and I create a larger node. That is, I will indicate this as a 0, and now this is free. So basically, when releasing, we are checking if the node's buddy is free. We merge them in a single node. So that is the task we are doing in make free function. So first we search for the. So in make free function, we are taking the node which is to be released, and then we are searching in this while loop. We are comparing the request with each tree node. If we find that particular partition, we are breaking and coming out, else we proceed to search for the next node. So this is basically linear search for the partition in the tree. Next, once we found the particular partition, we are freeing it by writing 0 to that particular node. And as I told you, we have to merge. If after freeing the particular partition, we should check if its buddy is also free. If its buddy is free, then we merge those two and make the parent as one larger partition and free it. So this is what it's doing until we reach the root node. That particular tree node is free, the one which we released now, and its buddy. That is, if this node is an even node, its buddy will be at location node -1. If it is an odd node, then its buddy will be at node +1. So is equal to 0. So its buddy is also free and this node is also free. In that case, you can see tree of node. If it's an even node, its parent will be node -1/2 or else it will be node by 2. That you are setting to 0. That is basically, if both the buddies are free, you are setting the parent node to free, indicating that now it's released. So it will be initially splitted, right? Now you are putting 0, indicating that now it's free. Now you are protruding up, or you are proceeding up in the tree node. So now your node is equal to node -1/2 or node divided by 2, depending upon the node, if it's a left node or a right node. So you do this. So this is what is the make free function. This is how you release the thing. Next, let us look at printing function. So this printing function, it's taking the total memory and 0 as an input. So here there are different steps here. So first thing is, in this particular node, in this if else, what we are doing is, if the node is initially 0, that is, we are starting with the tree node, then we are setting the perm value to 1. And if the node, basically what we are checking is, if the node is splitted, then we are going to proceed to display its content. If the node is not splitted, then we stop there. If the node value is 0, indicates that we need not proceed further down. It's not splitted. Hence, you can see here, for this is a special case of root node, wherein we are setting the perm to 1. Else, if it's an even numbered node, then we are checking if that if its parent is splitted, then the permission value is 1. If the parent is not splitted, then its value will not be equal to 1, right? So your perm value will become 0. So basically, in this particular case, you are checking if the parent is splitted. If the parent is splitted, only then there's a point in proceeding downwards. Else there's no point, right? Hence the perm value will be 1, set to 1 if the node is if the parent node is splitted. Else the perm value will be 0. So if it's an even node, you're determining using its parent node. Else you're determining using node by 2 parent as a parent. So basically, in this if part, you are setting the perm value to 0 if there is no point in further proceeding down the tree. Else it will be set to 1. Now, if perm, so if your perm value is 1, it indicates that you need to go down and print that particular tree, right? So initially we are setting ulimit, limit and tab to 0. And you'll get to know what it is. So infinite while loop. So you're checking your node. So the node is the node on which you are going to display the tree, right? Tree content. So initially it is 0. So 0 is greater than L limit and 0 is less than U limit, right? So it will break, right? It will break and it will come out and it will display. Here. You can see total to the 2 to the power of the tab value. Tab value is initially 0. So total memory divided by 2 to the power of 1. So basically you are displaying the total memory 2 to the power of 0, which is 1. So you are displaying the total memory, right? Else, if it is not the root node, if it is the root node,
it's going to display the total memory 1024. If it is not the root node, in the sense, the node value will be something else. Right, node value will be something else. In that case, what you're doing is this node value, if it is greater than a limit and node value is less than equal to limit u limit, until this condition is reached, you are going to increase the tab value. So basically what it is doing is you are going to determine until what level of the tree you are. So you're going to increase the tab and you are going to increment the L limit and U limit value. Basically, you're counting the number of nodes in the tree, right? For that particular level. You're counting the number of this thing. So once your node, you reach the particular node, this condition will be true, and you're going to break and you're going to come out. Once you come out, so basically in this green area of the code, you're determining at what level of the tree you are, right? At what level of the tree you are, and then that is determined by this tab, right? So now once you determine the tab value, you're going to print the size of the partition there, right? And now in this blue part of the code, you can see once you display the partition size, you're going to determine what is the content of the node. If the content of the node is greater than 1, it means that this particular partition has been allocated, right? So it prints allocated, and it prints what is the size of the memory that has been allocated. If this is not the case, if the tree value is not greater than 1, then if it checks if it is equal to 1. If it is equal to 1 means what? That particular node has been splitted, right? Hence, if it is equal to 1, it's going to print as it is divided. Else, it indicates if it is not greater than 1, if it is not equal to 1, it means it's equal to 0. Hence, you print there free. So in printing, it's very simple. Printing, there are 3 things. First thing is you determine if the node is splitted or not. If the node is splitted, then you proceed and determine the level in a level, and then you display the size, memory size as a you display the partition size, and you check if it is greater than 1. It means that particular partition has been allocated. If it is equal to 1, then it's divided, else it is free. After printing this particular thing, you can see here it's a recursive function. So you're going to continue this for your left part of the tree, and then followed by a right part of the tree. So this printing is a recursive function. Whatever I told, these 3 steps in the tree are repeated for the left part of the tree and followed by the right part of the tree. So this is the printing function. Let's execute this particular code and see. So here I have copy pasted this particular code, right? Now I'm going to run this. So I'm going to give 1024, right? I'm giving choice as 1. I'm giving the size of the process as 100. And then I'm entering the choice 1 again, and I'm entering the process size as 60, right? And then I'm entering choice 1 again, and I'm giving it as 240, right? And then I'm giving 1 again, and I'm giving the memory location as 250, same as what we had discussed in the example, right? So now I will give the thing as print choice 3 I'll give. So that's going to print the tree. You can see here 104 is divided, isn't it? Then 512 is divided, 256 is divided, 128 is allocated 100 if you recall. 128 is divided and 64 is allocated 60. So another 64 is free. Then 256. So like this, the program is able to display the memory map. You can check with free also. So this is what is the buddy program. Thank you.